Hello, everyone. My name is Javad, and I'm here with you with the 15th session of Bootcamps in GeoHackathon 2022. We are delighted to have you in the last Bootcamp presentation of the GeoHackathon, but obviously we have another Q&A session tomorrow, but today is the presentation Bootcamp. So today we have computer vision using MATLAB, and just to recap where we are on the schedule of the GeoHackathon, we are here, computer vision using MATLAB. And as you can see, Ayon and Oscar are here from MathWorks to have this presentation with us. And I would like to thank our sponsors during this GeoHackathon, and also especially MathWorks for having 4 different bootcamp sessions. So let's not waste more time and just give the and ask Ayon to start the presentation. You had Ayon for the last bootcamp. I think he spoke about image analysis, image processing using MATLAB. Today he's going to talk about computer vision using MATLAB. Ayon, floor is yours.
Thank you very much. Can everybody hear me? Okay.
Yes, we can hear you perfectly.
Okay, so I'm going to share my screen. Do you see my title slide? Awesome. Okay, welcome to the 4th MATLAB session and the 15th session overall, right? And today we're going to pick up from image processing and focus on image labeling, and then on semantic segmentation, a semi-automated labeling method, and then some transfer learning and an illustration of transfer learning. So once you've got labeled images, right, how you can modify an existing network and adapt it for your problem, for your issues. Right, we can just go through. Just wanted you to, if you have any questions, please type them in the Zoom chat. My colleague Oscar will be monitoring that. And we'll have a discussion at the end. So the objective today is to get started with solving computer vision problems through a real world example. Right, so why would we want to use MATLAB to do this? We have MATLAB is ease of use and thorough documentation, right? You can do rapid prototyping and algorithm development by leveraging the applications we have. And then this is not really part of the hackathon, but eventually you might want to deploy your solution. Right, so we have a complete set of algorithms and pre-built models to handle machine learning and the various deep learning approaches, and then even optimization of your hyperparameters, right? And then also put in regression, because all of this can be also applied to regression problems. Right, we have pre-built models that you can access, AlexNet, GoogleNet, SqueezeNet. These are just a few, right? And it's growing daily. And there's all kinds of reference examples you can go through. So at MATLAB, we really stress the increase in productivity by leveraging our apps, particularly in deep learning. We have a deep network designer app that allows you to graphically, right, easily build a network architecture, test it, right, and we'll analyze it and load some data in and train it. And then also we have what's called the experiment manager. If once you're happy with your architecture, you want to fine tune it, and you can check different things and sweep through all the different hyperparameters, right? It can keep a track of it for you here, and then you will be able to have an optimized solution. Right, so it's just a little video kind of showing the deep learning designer and then what's available, right, in terms of the preloaded or pre-trained networks, and then like you can um, explore and interrogate all the layers. It's a drag and drop system for building an architecture, right, where we can then analyze it. We see that there's no errors in this one, right? Then we might go to importing some data. And then we go to, then you can fully train. So this is a self-contained app that takes you from design all the way to a trained network. And then of course you can export or generate MATLAB code, so you can use it in a more complex system. Right, so today's focus will be on the image processing toolbox and the computer vision toolbox. And to whet your appetite, on your own, you can explore this computer vision case study a client of MathWorks used, and how they leveraged our tools, right, to improve their MRI accuracies. So image processing and computer vision should be thought of as two components that interact together. Image processing is sort of manipulating or preparing the data, while computer vision is leveraging or using the data. Here are some typical techniques that are used for sort of image processing and computer vision. The groupings can be a bit arbitrary, but this is typically how it can be split. We're going to focus on labeling and segmentation today. We have various labeler apps, available to help you label your images, or if you had video data or LiDAR data or medical imaging labelers, right? So there's a whole variety of apps available for all different types of problems. And this is an example of semi-automated labeling with the apps, right? So you can, this is focusing on like auto detection for vehicles. Right, and it shows, right, how you can label stuff after using some automation. I'm not sure why the audio is not coming through. Right, so this is if you were trying to isolate a human image. Here is isolating cars. And we will go through an example for this GeoHackathon challenge as well. And to do that, we're going to we're going to go to MATLAB. Okay. So here is a live script where we will explore some of the things that we've just seen. So first we'll prepare the workspace, and then we're going to get started with the image labeler, because this is what will be of relevance for the hackathon. And here's some information about the labeler, and then you can click through right, to get the full information and help you get started. So now we're going to take a look at the image labeler app. We're going to pull in some images where from last session we combined the cathode luminescence and the backscattered electron images, right? We're going to then also we're building a data store, which we went through in detail in the last session. And then we're going to load those into the image labeler, and we'll take a look at some of the options available to you there. So here's some combined images that we worked through last time. So let's first define some labels that we would want to label in our image here. So well, we know that we are interested in pores. We want this to be a pixel label because we want to label the pixels. We'll also want to label quartz. We'll want to label the overgrowth. And we'll also want to label the other mineralogies as it was brought forth in the introductory sessions that they are of importance too. For this particular problem. Okay, so let's look at some options we have to start labeling this. Let's start with porosity. So we'll pick the pore label, and then you'll notice across the top that there are various options. Well, I've noticed that the porosity, right, the black spaces, can be well defined, but they can also be pretty complex, like down here where we have porosity and other mineralogy interacting in a complex way. Well, with this combined enhanced image, right, the flood fill tool can help you with issues like this. So if we pick that, and then we pick the black, which we know is porosity, and we just click, you may have just noticed, right, it picked around all of these images. And like that, we can pick different porosities that exist. Now you'll notice that last pick misclassified some pixels in here as porosity. So if that happens, you just click on the erase. You can set the eraser size here, as you can see, and then you can just kind of clean up those misclassified pixels. We go back to flood fill, we can put this in again, right? We might want to clean up some of this stuff. Another option you'll see here is assisted freehand. This could be useful for labeling the quartz, because the quartz has very kind of large areas, and this will help you trace the edge. So if we like start here, you'll see the algorithm is automatically kind of following the overgrowth edge. And we can adjust it so we're getting right out to the edge. Now we've got some quartz identified. And then let's another thing you can approach the overgrowth in the same way, right? Or you could maybe you want to take advantage of the super pixel option, which is it will automatically discretize according to the edges that it detects, and then you can you have control over how fine the grid is. And then with that, then you can start labeling the overgrowth. There might be some situations like there where the pixels jump out. You might need to either take a finer grid or go back and erase some of these to get a better adjustment. And that's up to your own eye, right? You can make it as detailed as you want, right? So this is a way, this app really will reduce or optimize your labeling time, right? And which is always, right, one of the heaviest lifting or difficult parts of an image processing or of a computer vision project, right? And just for completeness sake, we can do some we can identify some of the other minerals. Okay, and then we would clear. We don't like that. We can just Control Z, erase it, and then do a better pick where we get most of that other mineralogies, right? And you can just kind of pick away. We know from our intro sessions that how to identify these things. And we would go through this, right, in a systematic manner, right, and label our images. I've done this for the 5 images that were provided and given to us as an example. And if I open the session I used. Now I did this before the bootcamp sessions began, so I did not isolate the additional mineralogies, right? But for the 5 that were labeled in the PDF, I came in and I labeled the combined images here. And we will use these, right, to explore semantic segmentation, which will then take your labeled images and then automatically, right, label the remaining images. And of course, right, there's no way ahead of time to know how many you need to label before an automated system will work to your satisfaction. And that's sort of the iteration aspect of this problem. So let's talk a bit more about semantic segmentation. Let me go back to my deck. So we've just seen how the image labeler app can help you label your images with your combined images using a variety of assisted segmentation, flood fill, super pixels, and then in the end, you can fine tune it by hand picking. Right, so now here's a little video about deep learning for computer vision, right, on how like you'd want your system to eventually like work. Just you'd want to be able to feed it images or video, and then it can automatically classify things. Right, and this is using AlexNet, which is a very common image classifying net. Some deep learning models, right, as we saw before, that are available to you are listed here. Particular of interest would be AlexNet, the VGG nets, right? And then we can get them in MATLAB just by in the tool strip or across the top, you'll see that there is an add-ons button, and from there you can download from within MATLAB, and then it's just a single line of code to access the models. You just you assign the models right to a variable, and then you can just go from there. You can also bring in, you're not limited to the MATLAB models. You can also bring in models from other environments, either through the Onyx interface or directly, some can be directly brought into MATLAB. Now, semantic segmentation is a methodology that works on organized data, and it's designed to take images, learn from them, and then segment remaining images. And for the hackathon, it's particularly important for associating pixels, associating the pixels to the label class. So let's go take a look in MATLAB for this. So if we go back to the script, right, we see that you have some labeler apps, right, that give you custom labeled data, and then you come in. We'll be coming down the pixel label training pathway, right, to train a semantic segmentation network. And of course, there's a link is included to get you started, right, and to take a look at the further details. Right, so for semantic segmentation, first we're going to prepare a data set, which is basically commands from the previous session. Then we're going to load the ground truth, which is the previous prepared labeled session that I showed, and that's how we're going to get the label definitions and the names. Then we're going to build a pixel label data store, and we're then going to before we get into semantic segmentation, right, just showing once you actually have your labeled data, right, you can then compute the fractions available. Now, of course, you're going to want to do this after semantic segmentation and classification of the blind data, but I just wanted to show you that once you have labels in images, it's fairly straightforward, right, to get the pixel count, right? If you just build a pixel label data store, and then you just run the count each label command, right? You'll get a table with the pixel count for each label and then the total image pixel count. And then from there, you can compute your quartz, your fraction of quartz, your fraction of quartz overgrowth, and your pore fraction just by extracting the relevant table value. So for quartz fraction, you would want the first row, second entry, and then the total image. So first row, third entry, and then as you go down, right, you just go down the rows. So for overgrowth, right, second row, second entry, and for pore fraction, right, third row, second entry. Right, so once you have a pixel data store and an image data store, you need to combine them. And then once we have that data store ready, we can do semantic segmentation. So MATLAB allows this or enables this in a very easy manner. You define the net you want to start with. So I'm using the pre-classified VGG 19 net, right? I'm giving it the image size, right? And then the number of classes. Now this would be 4 for the actual hackathon because we're also interested in the other mineralogies. And then this command in MATLAB, segnet layers, will build you a segnet, so a semantic segmentation network, using the weights, right, and the layers of your predefined or of your pre-trained and predefined network in just one command. And then this lgraph is what will be fed to the training command. So then here are some typical training options for a semantic segmentation. Because I only have 5 images, I've set the mini batch size to 1 just for illustrative purposes. But you will have many more than 5 images labeled, right? So then you can stick with the mini batch size of 4 or whatever you feel is optimal. And then we can assign the net to be, we want to retrain, right? Or we want to train the network with our data store and the new lgraph, which is a segmentation network, and then the options we set. So this is taking a moment to, yeah. So this is just an illustrative example. We won't be testing this network because it won't be very good just because it's only have 5 inputs, but it just to illustrate how it's going. Okay, this training is taking a long time. It's not finding my GPU. Okay, it's starting to come, but like this is a good example of showing how like a single CPU, right, might be not enough horsepower, right? So parallelizing, right, or having GPU access, right, will really help. I thought I had the GPU connected, but it doesn't look like this. So I'll just I'll terminate this now, but it's an illustration to show just to show how you would now be training the semantic segmentation network. And now I'm just setting it to stop because on the single GPU, I know it will take quite some time. And then while we're waiting for it to stop, we can go back to the slide deck. Right. So now we're going to talk a bit about transfer learning, where we can take a pre-trained network and then fine tune it for a new task. So transfer learning workflow is we load the pre-trained network, we replace the final layers, we train the network, we predict the accuracy, and then we deploy the results. So the first step is loading the pre-trained network. So you pick a pre-trained network and that you feel will work well for you, and you bring it into MATLAB. Then you will replace the final layers with new layers to learn for your specific task. One thing to note is that classification problems always end with 3 layers, right? A fully connected layer, which looks at the high level features, right? So this is where it adjusts to your particular problem. A softmax layer, which is just converts the scores into probabilities, and then it goes into classification. And then as a note, for a regression problem, it would just be a fully connected layer and a regression layer. Then, of course, we would train the network, and we would assess it, and then we would deploy it. Let's go back to MATLAB. So to illustrate transfer learning, we're going to look at a different type of problem, or a different example. This is classifying parasitic infections in a blood smear data set. Now, and this is a fully detailed example of how to use deep learning. And it's done in a programmatic way, but right at the end, we'll look at how we can take a look at deep learning. But I just wanted to show this goes through, like last week, a full workflow where we access the data and prepare it. We take a look at the distribution. We take a look at what the images look like. Right, we're going to do transfer learning specifically off of AlexNet. Right, first thing you want to do is look at the first layer to see the image size that your preset network is trained to handle, and then you'll have to resize, right, your images to that size, right? So they'll be ready to feed into the pre-trained network, and then you can go into adjusting the network at the end, which is what's being done here. And then we go through some steps to balance out the data and stuff as we discussed last week. And then we're augmenting the data to give it some more variety so it can be more robust when it learns. And then we get down to preparing the network for transfer learning. And this is specifically, right, we want to get the layers out of the net. We want to change the third from the end layer to a fully connected layer with 3 outputs, right? So for the classes that are involved, it would be 4 for the GeoHackathon challenge. And then we want to make the last layer a classification layer. And then we would go into training the network. Now this was all done programmatically, and we can then check different how it behaves, how it classifies. Right, the actual label is babecytosis. Forgive my pronunciation, and then we classified it correctly. But what we're really interested in is using the Deep Network Designer, or leveraging that. So to do that, we go, and first we would go to add-ons, and we would then download. We would get the add-ons, which would be the different add-ons that are available. And then you can see there's all kinds of stuff you can add to your system. And then as you go down through this, you will find networks that are available that you can load. And then we'll go into the apps. We'll go into the Deep Network Designer app. Right, so we'll start with a blank network, or you can start with any of the available networks. And in fact, since we're going to transfer learn off an AlexNet, we could just actually open one of these pre-trained networks. So we can go look, and we can find AlexNet. Bring it in. We can zoom in. To read what the layers are. And if we click on the input image layer, yeah, we see that it's 20, that the size of your images need to be 227 by 227, right? So if you were doing this in the graphical using the apps, then we would go back out to MATLAB to resize the images, because if we change the input image layer, that cascades and affects the other layers. So you need to resize your images to what your pre-trained network is conditioned to handle. And then you go all the way to the bottom, and we see that for the AlexNet, right, it's classifying 1,000 different classes, and it's outputting 1,000 different classes, right? But that's not what we want. We want to classify 3 and output 3. So just to do that, you can just drag and drop, right, a fully connected layer, drag and drop a classification layer, delete the 2 layers that we are concerned with, and then change it. We want 3 classes. There's nothing to set in the softmax layer, and then in the output layer, it's automated. So once we've built a new architecture, let's analyze it. Let's see how how it looks. And we see that there's almost 57 million learnable parameters in this architecture of 25 layers. And our transfer learning modifications work because we got no warnings and we've got no errors. And then we can go into the data and we can import data. So the designer app is self-contained. It allows you to design and train train your data. So we'll just bring in we'll bring in the augmented images we did, and then some validation data. If you do not bring in validation data, your methodology will quite likely be overtrained. So I highly warn against training networks without validation data. And then we can explore this, what some of your training data looks like. This is what some of your validation data looks like. Then if we go to training, we can then set the training options. As we did programmatically, you can also just fill out the the parameters. I just need to I just want to match this properly. So we set our learning rate to this value. We're setting our epochs, our max epochs to 15 and our mini batch size to 4. So to do that graphically or in the app, you just open up that. Okay, you can see it remembered. And then like that, we've set our training parameters, and then we can train. Now this might take some time just because of the fact that, again, okay, see now it's finding the GPU. So I don't know why it didn't before. Right, so then you can see we did a pretty good job with the transfer learning, right? Just by augmenting the images and resizing them, right? With that pre-trained network, right? In 12 seconds on a single GPU, right? We got it to 80% accuracy. Now, if we go back to the slides, okay, you'll probably want to improve and understand your network accuracy, right? So if you're getting some incorrect results, you'll probably need to label some more data to get a better semantic segmentation result, right? Think a bit about augmenting the data, the quality of your data, right? Did your noise reduction work as well as you'd hope? Did your combination work as well as you hoped? Did your image enhancement work as well as you hope? Then you can check results through the experiment manager, right? You can consider some questions to consider for your architecture are what layers are being used and why, if you've got like a deeper understanding, right? Are you normalizing the data? Are you regularizing the net? Right, what's the quality of the data? But typically your improvements are going to come here with the parameters and their settings, in particular, batch size, learning rate, and well, the weights will come through the backpropagation, but typically batch size and learning rate will have a very, very large impact. And then of course you can click out to this page, which will help you with why your net might not be working. And then you want to, of course, hyperparameter tuning, right? And as we said, like epoch, learning rate, iterations are all issues to explore, right? There's no magic number for each. Highly recommend this toward data science article for guidance with hyperparameters. So as a summary, we've with computer vision and MATLAB, we've got comprehensive documentation, ready to use algorithms, interactive live scripts and apps, and deep learning ramp up in MATLAB is easy. So some next steps you might want to consider is exploring the computer vision toolbox, a free deep learning on-ramp 2-hour tutorial, right, to familiarize you with deep learning, and particularly there is an entire module on transfer learning, right, to really prepare you, right, for building a solution, the GeoHackathon. And then of course you can get a product trial by getting a free license, or if you prefer, you can work on MATLAB online for 20 hours a month. And of course, you'll be exploring the deep learning toolbox. With that, I thank you